Howdy. I wanted to extend our discussion of Riemann sums today. And in order to do that, I'm going to need to first of all talk about some popular summation formulas. And we're going to use these later in the lesson. And what they do is they consider some common things that we could add up. I'm going to sum up from I equals 1 to n, and the first thing we might just add is 1. If I add 1 to itself n times, what do you think I'm going to get? Yep, you guessed it. I'm going to get n times 1, because that's really what multiplication is. Likewise, I can consider the sum from I equals 1 to n of I. And that would be equal to 1 plus 2 plus 3 plus all the way up to n. Now, this sum is very interesting because it has a famous result. Its value is equal to n times n plus 1 over 2. And one of the people, this formula has been known for a long time. And there's a famous story about Gauss that he discovered this as a 10-year-old. And he discovered it by taking the sum and writing it backwards. And if I write it backwards so that I'm adding the numbers from n down to 1, and I add it to the original, and what I get on the left-hand side is 2 times the sum. What I get on the right-hand side is very interesting. I get n plus 1 in the first term. In the second term, I get 2 plus n minus 1. In the third term, I get 3 plus n minus 2, which is the same as n plus 1. And all the way down the line until the last term, where again, I get n plus 1. And you can see that every single pair of terms must add up to n plus 1, because in the first sum, my terms are going up by 1, and in the second sum, my terms are going down by 1. And so those two effects cancel each other. Well, how many of these n plus 1s do I have? I have exactly n of them. And since n times n plus 1 is equal to 2 times my sum, I can divide both sides by 2, and there's our formula. Ta-da! It's kind of nice. These numbers, the sum from I equals 1 to n, are very popular and common, and sometimes they're called the triangle numbers, T sub n. And my favorite example of a triangle number is actually bowling pins at an alley. If you go bowling at all, then the pins are arranged with 1 pin, 2 pins, 3 pins, and then 4 pins. So the number of pins here is equal to the fourth triangle number, which is 4 times 5 over 2, or 10. There are a couple of other summation formulas that we're going to need. I'm going to give them to you without proof, but if you wanted to prove them, it's not too hard to prove it by induction. If I add up all of the numbers from 1 to n squared I squared, that is 1 plus 4 plus 9, all the way out to n squared, then it can be shown that this is equal to n times n plus 1 times 2n plus 1 all over 6. And if I add up the sum of cubes, 1 plus 8 plus 27 plus all the way up to n cubed, it can be shown that this has a value of n times n plus 1 over 2 quantity squared. So these summation formulas, these 4 summation formulas, the sum of I to the 0 power, I to the first power, I to the second, and I to the third power, are extremely useful to us, and you'll see why in just a few moments. Well, having established the summation formulas, I'd like to go back to what we talked about today in class. Today we used Riemann sums to estimate what we call net signed area under the curve. And we understand that under the curve really means curve than the x-axis. So for example, if I have a function that does something like this, and if I can find out that from here to here, the net signed area is 6, and from here to here, let's call this B, the net signed area is -4, then the total net signed area would be 6 minus 4 over 2. And we're trying to compute this, and the way that we did it was by estimating with a Riemann sum. First, we partitioned the interval from A to B in some way or another, and then we made a choice of C in each subinterval and constructed rectangles. Here I'm just going to construct kind of randomish rectangles, whose height was f of c sub I, and whose width is delta xi, and so the Riemann sum is equal to the sum from I equals 1 to n of height times width. And the Riemann sum is going to be an estimate of the area. We defined a couple of terms. We said that the mesh size of my partition is the maximum width of the delta xi. And we said that certain choices of ci gave us special sums. The left sum happens when I let ci equal the leftmost x value in the partition, or xi minus 1. The right sum happens when I let xi be the rightmost x value, or x sub I. The midpoint sum happens when I let ci be the midpoint of each subinterval, like so. And I said that these three are useful for computational purposes. If I have to do a sum by hand, I'm going to do one of these three. I also said that there were two theoretically useful sums, and one of them is the upper sum, which I'm going to give the symbol u. And the upper sum is chosen so that f of ci is the max on the interval I sub I. And the lower sum is going to be the sum that you get when f of ci is the minimum possible value on I sub I. We're going to give that a symbol L. And so now I want to make a couple of intuitively obvious observations, and then we're going to talk about how to use U and L in order to get an exact value for the area. The first observation that I want to make, and we can call this a theorem, but I'm going to give it without proof because it's sort of obvious, is that the lower sum is always going to be less than or equal to any Riemann sum that you can construct on a given partition. And the reason for it is fairly clear, and that is that in each of my rectangles, I'm choosing the smallest possible height for the lower sum. So therefore, each rectangle has to have an area that's less than or equal to any other way of choosing that I could possibly mention. And likewise, the Riemann sum is always less than or equal to the upper sum for a given partition. So that's our first important thing. And then I also want to define the error in our estimation as the absolute value between a Riemann sum and the true area, right here. And the error has a visual representation. If I take a curve, f of x, and I'm going to try to estimate the net signed area from A to B, and let me do a really simple partition, and I'll do an upper sum on this partition, so that we choose the max on each subinterval. There we go. Then the error is going to be the amount that my Riemann sum overestimates or underestimates the net signed area. It's all the shaded stuff that you see right here. And what we would love to do is to drive that error down to 0 if we can. And I want to observe that the easiest way to do that, or the smartest way to do that, would be to use skinnier rectangles. So I'm going to just appeal to your intuition that if the mesh size of my partition decreases, let's not go to 0 just yet, then the error should decrease also. Let's do that here. I've got this partition, so I'm going to now subdivide it. Sometimes people call that refining the partition, by taking each subinterval and dividing it into smaller subintervals. And if I now do an upper sum on my subdivided partition, then you can see that while I did not eliminate all of the error, I did eliminate a fair amount of the error. All the shaded stuff is error that is no longer part of my Riemann sum. And so I've improved my estimate by decreasing the width of my rectangles. And to do that, I had to have more rectangles. So there you go. Here's what we're going to do. We're going to let the mesh size go to 0 in our upper sum. And we're going to let the mesh size go to 0 in our lower sum. Now, I didn't specify how yet that we're going to do that, and I'm just going to ask you to trust me that this makes sense. We're going to let the mesh size go to 0, and when we do, we're going to use the notation for this as the upper integral from a to b of f of x dx. And when we let the mesh size go to 0 on the lower sum, we're going to call that the lower integral from a to b of f of x dx. And now here is a thing that seems intuitively obvious. If the upper and the lower integrals converge to the same number, that is, if the upper sum and lower sum have the same limit, then that is going to force all of the Riemann sums that you could possibly construct to go to that same value. Let's call that value A. And in fact, that value A is the net signed area. In other words, we're going to eliminate the error by making my delta x so small that there is essentially negligible error left. Now, the notation that we're going to use for this then, the limit as the mesh size goes to 0 of my Riemann sum, is going to be the integral of a to b f of x dx. Let me take a minute to explain that notation. Remember that the Riemann sum can be written as the sum from I equals 1 to n of f of ci from delta xi. And in Leibnizian fashion, in fact it was Leibniz that introduced this notation, what we're going to do is to think as the delta x's go to 0, and notice that if the mesh size goes to 0, all of my delta x's must go to 0 with it. As the delta x's go to 0, then they are going to become infinitesimally small pieces of x. This is Leibniz talking. And as the delta x goes to 0, my choice of ci gets limited because the width of the interval that I can choose over it now shrinks to 0, so that I really only have one choice, and that is to choose x at each subinterval. And Leibniz is going to take this capital Greek S, and he's going to write it as a stylized Gothic S, just like so. And so the notation here is very suggestive. What Leibniz is doing is he is summing up differentials. And each differential, f of x dx, represents a little tiny skinny rectangle whose height is f of x and whose width is this infinitesimally thin dx. That's how Leibniz is thinking about it. Now you notice that this has a notational resemblance to our antiderivative. That's not a coincidence, but it's going to take next week to explain that. So, there's our theory. We are going to evaluate these areas by constructing a Riemann sum and letting the mesh size go to 0. That's the plan. How does this actually work out in practice? I'm glad you asked that question. I'm going to answer this question in 2 stages. Stage 1 we're going to do in this video, and that is that we're going to compute net signed area for simple polynomials. That one we can do by hand. In stage 2, we're going to recognize that computing these definite integrals with a limit turns out to be a real pain in the neck. And so we're going to need a theorem, and the theorem that's going to help us is going to be the fundamental theorem of calculus. And that's going to allow us to evaluate these definite integrals with antiderivatives. For this video, I'm going to focus only on stage 1 here, simple polynomials. And our plan is going to be this: to evaluate the integral from a to b of f of x dx. First of all, I'm going to construct a Riemann sum. And then, having constructed the Riemann sum in terms of an arbitrary number of rectangles n. Once I've constructed that sum, I'm going to write the Riemann sum in closed form using our popular summation formulas that we talked about at the beginning of the lecture. And then, having done so, I'm going to let the mesh size shrink to 0, and that's going to give us our area. That's the plan. Let's see how this actually works out. Let's find the integral from 0 to 2 of x squared dx. If we sketch what's going on, here comes my curve y equals x squared, and what I'm doing is going from 0 out to 2, and I'm trying to find all that net signed area. So I'm going to go through and I'm going to construct a Riemann sum, adding up these little tiny differential pieces of area, f of x times dx. And to do that, as we saw in class, the first thing that I need to do is to partition my integral. Now, here's the really cool thing about this. Because the upper and lower sums are bounds on all Riemann sums, it doesn't matter which Riemann sum I pick. I can pick any Riemann sum, and as delta, the mesh size goes to 0, I will get the same value. So I might as well pick an easy Riemann sum. I'm going to choose n equally sized subintervals. And so when I do, the delta xi is going to be b minus a over n. Easy peasy. Once I've chosen my delta xi, the xi are chosen for me. That's going to be the first x value plus I times the delta x. And so those give me the xi's. Now, having chosen my partition, next I want to choose a summation method. I could choose left, right, mid, I could choose upper, I could choose lower. The right sum is probably the easiest, because in the right sum, my c sub I is equal to my x sub I, and I already know what the x sub I is. So, if I do that, then my sum is going to look like this. The Riemann sum for n rectangles is the sum from I equals 1 to n of f of ci times delta xi. And now we're just going to go through and substitute. F of ci is going to be equal to f of 2i over n, and my f of x is x squared. And the delta xi is 2 over n. And there it is. I can clean this up a little bit. And that gives me 4, no, it actually gives me 8 I squared over n squared. Okay. Well, this is the Riemann sum. So in terms of our plan, back over here, we have constructed the Riemann sum. Now what we'd like to do is to write it in closed form. And the reason that we need to do that is that we are going to let the mesh size go to 0, and we're going to need some closed form to work with, because we don't know how to do limits of sums very well at all. To do that, I want to observe that both the 8 and the n squared are constants with respect to the variable of summation, which is I. And so I can factor those out of the sum. And when I do, I'm left with something that is familiar. It is the sum from I equals 1 to n of I squared. And I've seen that one before. Going back to my popular summation formulas back on the first page, I can see that the sum of I squared is equal to n times n plus 1 times 2n plus 1 all over 6. And so I can take and copy that form directly into here. And this is the Riemann sum for n equally spaced rectangles using a right summation. If I were to, let's see here, I've got n squared here. This n squared is wrong. This is n cubed. If you've been suffering through that, please accept my apologies. There it is. This is the Riemann sum for n equally spaced rectangles using the right sum. So if I were to choose, like n equals 6 and plug into this formula, that would give me a right sum for 6 rectangles. What I want to do is that was a little more ambitious. What I'd like to do now is to take the limit as the mesh size goes to 0. Let's explore that a little bit. Remember that our delta x is equal to 2 over n. And so if I want this to go to 0, then really what I want to do is to let n go to infinity. Because my rectangles are equally spaced, therefore letting the number of rectangles become infinite is going to guarantee that the mesh size will go to 0. And wouldn't you know it, this limit becomes easy to evaluate using n models. Because this is 8 over n cubed, and this is going to be n times n times 2n, or 2n cubed, all of that over 6. And when the dust settles, the n cubes cancel, and I get 16 over 6, which is equal to 8 over 3. And this is the exact area, the net signed area under the curve. So our plan was, just to review all of this, first we partitioned and constructed our Riemann sum. The right sum was the easiest choice here. Having constructed the Riemann sum, we used our summation formulas to get it into closed form. And having done that, we evaluated the area by letting n go to infinity, which guaranteed that our mesh size went to 0. Let's do one more, and then we'll call it an evening. Find the area under y equals 3x plus 1 from x equals 0 to x equals 4. Let's sketch this to see what's going on. Here comes my straight line y equals 3x plus 1. And I'm going to go from x equals 1 to x equals 4. And so we're looking for this net sign area right here. Now, if you noticed already that that is a special geometric shape, then good for you. We'll use that fact to check our result at the end. Remember the plan. First of all, we're going to construct our Riemann sum by partitioning by choosing CI and substituting into the form. So for our partition, again, it is easiest to use equal size subintervals so that my delta x for n rectangles is going to be 3 over n. And the xi that come from that are going to be the initial x1 plus I times the delta x. The choice of CI, again, we could do anything, but the easiest choice is probably to do a right sum. Like so. So that when I do, I can now construct the Riemann sum. R of n is going to be the sum from I equals 1 to n of f of ci delta xi. I strongly recommend writing out this form because the more you write it, the more it will become ingrained in your consciousness, and then it's just a matter of substituting in. The delta xi we already have, that's equal to 3 over n. The f of ci we can compute because we have f of x, which is 3x plus 1, and that's going to be evaluated at xi, which is 1 plus 3i over n. So we get 3 times x plus 1. All of this is multiplied by delta x. And now we're going to sum up from I equals 1 to n. This is really the only complicated part when you're doing it. You just got to make sure that you're substituting correctly here. This right here is the xi, and this whole quantity right here is the f of xi. Well, let's clean up and see what we have. This is the sum from I equals 1 to n of, looks like we're going to have 3 plus 9i over n plus 1 times 3 over n, which is going to give me 4 plus 9i over n times 3 over n, which is going to give me now the sum I equals 1 to n of 12 over n plus 27i over n squared. And this is the Riemann sum simplified. We've got it simplified, but we don't yet have it in closed form. So that's our plan from here. And to do that, we're going to use typical summation kinds of things. First of all, we're going to split up our sum using commutative and associative properties. And then we can factor out any constants in our sum to set ourselves up to use the summation formulas that we know and love. And in the first sum, I'm summing up 1 from I equals 1 to n, which is just going to give me n. And in the second sum, I'm summing up I from I equals 1 to n. And if you go back to the summation formulas, you may remember that that was n times n plus 1 over 2. And so we simplify it a little bit. We get 27 over 2n, 12 plus 27 over 2n squared times n plus 1. And we could, if we wanted to, simplify it a little bit further. But the point is that we now have a closed form for our Riemann sum for n rectangles. And so this was the hard part. The easy part now is to get the area as the limit as n goes to infinity of Rn, which is the limit as n goes to infinity of 12 plus 27 times n plus 1 all over 2n squared. And you can see pretty easily that that's going to be equal to 12 plus 27 over 2. Or if I would write it as a single fraction, then that would give me 51 over 2. Now, because this happened to be a special shape, we can actually check ourselves and see how we did. because this is a trapezoid, I can do the area as the width times the average of the bases. And the base here is going to be 3 times 1 plus 1, which is 4. And the base here is going to be 3 times 4 plus 1, which is 13. And so the area, the exact area should be 13 plus 4 over 2 times 3, which is going to be 17 times 3 over 2, which is equal to 51 over 2, which is exactly what we got for the Riemann sum. I hope this was interesting to you.